So thank you very much for the patience. My name is Nico Pizzo. Can you hear me in the back now? You can't hear me? No. So I'm going to talk about the wave momentum myth better. Right, like this? Okay. So this is work done with my colleague and friend, Greg Wagner. This was kind of a conversation, kind of an argument, as any good conversation with Greg is. Sorry, it's auto playing. Stand by. So to motivate this, we're going to consider what the ocean looks like. If we can watch this video. Stand by. So this is 100 miles off the coast of San Diego. We have waves propagating from the upper left to lower right. Quite a bit going on. There's some longer waves propagating through the screen. Some shorter waves traveling almost orthogonal to that. Where the waves steepen, they ruffle. The waves overturn and break. I want to keep the complexity of the ocean in mind while we talk about this very idealized problem. It's good. And we're going to talk about momentum pathways from the atmosphere into the ocean. And so we'll start by collecting some basic information that we know, and that's for periodic, irrotational, deep water, inviscid waves, they transport mass. So if you look at the particle trajectories, they're not closed circles, they're slightly open. This implies a net drift in the direction of wave propagation, whereas the Eulerian velocity field is perfectly periodic. So if you were to define the difference of the Lagrangian and Eulerian mean as something we're going to call the Stokes drift, you would see here that it's non-zero and it attenuates with depth. This is that evanescence that we've been talking about. Keep going for the wrong computer. So what does Stokes drift look like for a typical ocean spectrum? So these are those LiDAR measurements from Luke that we saw earlier on a day not unlike the one in the video on the right, 10 meter per second, 10 meter winds, peak period, 10 seconds. And Kern Kenyon, who was one of Hasselmann's students when Hasselmann was still in San Diego, showed us how to compute a spectrum from these omnidirectional wave spectra. It's quite large at the surface, 20 centimeters per second, and it rapidly attenuates with depth. At 5 meters depth, we have about 10% of the value we do at the surface. And what we also know, and has been hinted at, is as soon as the free surface becomes deformed, most of the momentum does not go into driving a current. It goes through the wave field. And in the Lagrangian reference frame, this wave momentum is exactly in this drift for periodic waves. For wind speeds above about 6 meters per second, almost 100% of that wave momentum is then redistributed. If I keep doing this, it's not going to work. And if you're still awake, here's a high-speed video that Luke Linane took of an overturning wave. It's not Martin and Duncan-esque, but it's the Scripps version. The wave overturns and breaks. It topologically changes the fluid, introducing vorticity. This is that divergence between the mathematical models and reality that we were talking about a little bit earlier. And it is redistributing, not creating momentum from this breaking event. So now we want to ask a question, and this is the central motivation of this talk. What is the momentum pathway between the wind and a wave packet? And so you might be asking, how can this possibly change? So let's assume that the wind works on the water in some way, and it imparts some momentum I from the atmosphere into the ocean. Well, Long and Higgins and Stewart taught us, in a very difficult way, that wave packets in isolation have a long wave response. So basically, the waves are propagating this way, the carrier waves. They pile up mass here. There's less mass here. It drives this long wave response. And Long and Higgins and Stewart taught us that the sum of the momentum in the waves and that in what I'll call the long wave response have no momentum. But we just said we're putting momentum into the fluid. So the question is, where does it go? And there's been quite a bit of work done on this. Sorry. And so this was what partially Michael McIntyre was trying to do in this paper on the wave momentum myth, which I'm kind of playing on this title. This paper derides everybody for being unable to understand basic arguments about momentum in fluid mechanics and then makes it super, super confusing. And so the point of what Greg and I did, and if we write a paper, we won't start with a quote, I promise, is to try to clarify some of what's going on with this description. But it's worth noting that what McIntyre argued, and it's based on an earlier argument from Benjamin, is that The waves and the packet are deep, but the water's still finite. And as these wind is generating these waves, the momentum's going to propagate away in these short waves. And so Greg and I found this a little bit weird. Okay, maybe the short waves, or sorry, not the shallow water waves, can carry away some of that momentum. But it seems a little odd. We're talking about waves not having momentum. Is there some kind of return flow associated with those shallow water waves? What's going on here? And so that's one of the points of confusion we had. The other is that when these waves approach shore and the length of these groups L divided by the depth H is no longer small, these packets have momentum, basically because the free surface has to change. And so this introduces the two gaps in knowledge we're trying to fill, which is what if everything's in deep water? What if we start where H is infinite, there's no such thing as a shallow water wave, and we force the free surface? What's going on with the momentum? The next question is, what happens as these packets approach shore? So how is momentum conserved if we start with a packet that had no total momentum in deep water and non-zero momentum in shallow water? How is this possible? And so to answer these questions, we are going to work in the Lagrangian reference frame. And this is useful because in 2D, vorticity is conserved along fluid particles. And the vorticity is very strongly constrained in fluid mechanics. So it's going to give us a tight constraint on what's happening with the mass that's based on the physics of what's going on in the scenario. But when you do a deal with the devil, you got to pay something. And that's we abandon a lot of very powerful classical tools like analytic function theory, which is very powerful in the Eulerian frame. So we'll start by talking a little bit about the Lagrangian frame just to introduce it. Our independent variables here are the particle labels A and B. Label space is very simple. This is kind of what Daniel was talking about yesterday. He was mapping some complicated physical space, x, y, to some less complicated lower half plane. This ends up being useful when you're averaging. Eulerian averaging can be very clumsy, especially near a free surface. If you took some phase average here and you talked about something happening at y equals 0, this point would be inside and outside of the fluid half of the time. So how do we interpret something like this? So we're going to write down our equations of motion, starting with the conservation of mass, or the continuity equation. We're going to change variables in the normal way using notation defined here. These are determinants of Jacobians, and I'm going to define them in terms of a bracket. What we need to know is in the Lagrangian frame, mass conservation says that the bracket of x and y is some function independent of time. For this, it's basically telling us that if the density is constant, and we have some chunk of area, it's not changing size. So geometrically it makes sense, but we're not saying anything about what this function j is. We can label particles however we want. This is a gauge invariance of fluid mechanics, and it's very powerful. It corresponds to a particular symmetry that implies conservation of vorticity. So this is kind of like one of the fundamental aspects of fluid mechanics. At a practical level, choosing gauges, just like when we were in E&M in undergrad, can really greatly simplify the analysis of a problem. We can also write down the momentum equations, which are in chapter 1 of LAM, and I seem to be going back in LAM as I say in fluid mechanics. And we can eliminate the pressure between these two momentum equations to write down, as advertised, that the vorticity Q is conserved along fluid particles and can be written very simply as such. We require that the pressure is some prescribed value at the surface. If we're forcing the surface, this is something. If we're not, we're going to say it's 0, and there's no flow through the infinitely deep bottom. And so from our equations of motion, we can derive conservation laws in terms of the momentum I, the radiation stress, so the momentum flux S. If the pressure is 0, this is 0. These are actually conserved then. If the pressure at the surface is not, we're putting momentum into the system. And we can do the same thing with the energy. These non-calligraphy values I, S, E, and F are just the integrals of these densities, either over a period or over some larger distance, in the, depending on the scenario under consideration. And so to solve this system, you do the normal thing. We're going to do asymptotics on the particle labels x and y. And on the pressure, we have an asymptotic parameter, epsilon, which is much less than 1. And we fix the gauge to just be 1. So basically we're thinking about area preserving maps. It's not a great gauge, it's the easiest one to guess, and it's sometimes called Mish's condition, but it's sufficient for what we're doing here. So to get intuition, we're going to start with the unforced problem. So we're going to take the pressure to be 0. And at 0th order, we just have hydrostatic balance. We know how to do that. At first order, our equations are fairly simple, and we can solve them. They tell us that x and y are wavy, and they have some amplitude that can vary slowly in space and time. And because these are real, k and omega can also vary slowly in space and time. We don't have to worry about that too much. The pressure at this order is 0. Recall, we're not forcing our system. And the waves obey the linear dispersion relationship. We can then go to second order and get some equations for our mean flow, our second order things that we're trying to look at in terms of a conservation or continuity equation and a vorticity equation. We can differentiate mass conservation, and that implies that we should define some stream function psi. So that automatically satisfies this top equation, whereas the second equation becomes just Poisson's equation for the stream function associated with the mean flow of this wave packet. So you have the Laplacian of psi is equal to something on the right-hand side. The first thing we note is if we zoom out and these packets are compact, this wave packet kind of looks like a source for the mean flow response. And the second thing is from the horizontal momentum equation, we can derive a boundary condition which tells us that the mean flow essentially sees the surface as a rigid lid. So what is this term on the right-hand side? If you know anything about generalized Lagrangian mean theory, it's nothing more than the curl of the pseudo-momentum. Okay, what the hell does that mean? We want something that is associated with the energy, which is not going to vanish, unlike the momentum. The pseudo-momentum is related to the wave action here, and it tells us a lot about what's happening just near the surface. And so we see that this curl of the pseudo-momentum is a source of this long wave response. And it's ironic that we're talking about irrotational waves, and I keep talking about vorticity. And when you work in the Lagrangian frame, this is what happens. Even if the vorticity vanishes, the vorticity equation ends up telling you a lot about what's going on. And so we can integrate very quickly the horizontal momentum and do it and just write it down in terms of the stream function, which we just talked about. And we know that it vanishes, which is what Long and Higgins and Stewart told us. But we can also compute things like the radiation stress and the energy and show that they don't vanish. And so what's nice is we haven't really solved very much. You can go through and solve for a local particular solution and a non-local homogeneous solution. The particular solution is nothing more than this classical Stokes drift. It's just this Lagrangian mean flow right below the wave packet, whereas the homogeneous solution is irrotational, but it has some source at the surface. And you can solve for this using the theory of Poisson integrals at the surface. These are related to Hilbert transforms. But again, we don't have to solve things like this, and in fact, we kind of can't. So this is really nice, because we're doing analysis without actually having to know the exact solutions. And then we can think about what happens if there's some wave propagating, like we were watching in those videos earlier. It has no momentum. Something happens, like an impulsive forcing event, like braking. It peels off some of the momentum from the carrier waves. And the way the system has to respond is to leave and jettison some of the mean momentum of the long wave behind so that the total momentum remaining is still 0. And so this is something to kind of turn over, but it's just imposing the fact that momentum is not being created or destroyed here. So now we can go through, I just have a few more minutes, and look at the forcing of a deep water wave packet. We assume the pressure forcing is exactly in the form of some wave packet. It varies slowly, it travels at some group velocity. We can go through and play the same game we did for the unforced case. You find the vertical dependence of the pressure. That's not particularly interesting. To find the temporal behavior of the waves, you substitute in the pressure, and you get these equations essentially for forced harmonic oscillators. Because the pressure is in the kernel of these operators, you get secular solutions. And it just tells you that x and y grow linearly with time. This is exactly analogous to what Lamb talks about in the Eulerian context from generating waves. And this is assuming that at t equals 0, the surface is flat. So what happens at second order? We can write down equations again. You can't write them in terms of a stream function, but you can write down things in terms of the Laplacian of the horizontal velocity and vertical velocity, and write down a boundary condition. And what you get when you run through this exercise very quickly is that the solution of the force system tells you that all of the flow is in this mean Lagrangian flow associated with the drift. There's no long wave here during the forcing event. And so, because everything's linear, and we recall that in the unforced case, there's this long wave response, what this is telling us is that during forcing, there's an equal and opposite long wave that's exactly canceling the normal long wave we'd expect in the unforced case. And so if we turned off forcing, we put in some momentum into the fluid, we turned off forcing, then in the region we turn it off, this dipolar structure with some momentum I naught is stuck there. It can advect under the action of its image and the free surface, whatever. It's not going to move very much, whereas the wave packet and the long wave response are going to propagate away. So the last thing we want to consider is what happens when waves propagate towards shore. In finite depth, they have momentum, as Long and Higgins and Stewart taught us. In deep water, they don't. What's going on? We can think about some change in water depth, some step from infinite depth to finite depth. And the only thing that can happen, and I haven't finished these computations, this is a hypothesis, is that to cancel the momentum that's now in this wave packet, we must bound some of the long wave in this region on this step so that the total momentum in the system is conserved. Okay, that's it. I know that was 60 slides in 17 minutes, so yeah, thank you. But that's it. Thanks.